Hello everyone, I welcome you all in this course Introduction to Sequence Stratigraphy, and as we were discussing in our previous lecture on the transgressive refinement surface. So, in this class also we will continue our discussion on that topic and we will try to understand about the different aspects of transgressive refinement surface. So, already we know that there can be two types of transgressive refinement surface. One is a wave refinement surface which is more dominant, and we can have a tidal refinement surface. So, in the rock record, commonly the wave refinement surface is more easily identified, more easily available, particularly when we look at the vertical profile. There this wave refinement surface very often superpose on the tidal refinement surface, or that completely overprint the tidal refinement surface. This is just because all these are forming during a retrogradational phase, during an onlapping phase of the transgression, where gradually the seaward processes, the seaward conditions, they are onlapping, they are encroaching onto the landward processes, landward conditions. So, whatever formed in the landward side in the earlier phase, they may got either covered up or they may get reworked by these marineward processes. So, as a result of that, already in the last class we have seen the tidal refinement surfaces, they will form more towards the landward side with respect to the wave refinement surface. And if, say for example, in an estuary system, if the estuary gradually onlaps, if the marine system gradually onlaps on the estuary, then this wave refinement will cover up or overprint the tidal refinement surface. So, these transgressive refinement surfaces, they are often very useful in terms of their associations with characteristic ichnoforms, because they are often very much favorable, they creates very much favorable conditions for the formation of substrate controlled ichnofacies, because these surfaces they act as omission surface which are always covered and are overlain by marginal marine to shallow marine deposits. So, those marginal marine or shallow marine deposits, they are the most favorable zone where the substrate controlled ichnoforms, substrate controlled ichnofacies can be found very easily. Now, along this particular surface, depending on how much scouring is going on, whether it is a tidal scouring or it is a wave scouring, and how much of gap is there in terms of the sedimentation process, because when erosion is going on, definitely it is a gap in sedimentation, and that erosion, that scouring will lead to some sort of new surface available, some sort of modified substrate condition available apart from the substrate control condition, and that can lead to characteristic ichnofacies. For example, in some areas we can get farm grounds, particularly those areas which remain exposed for some time, and when there will be farm ground we can get glossy fungi ichnofacies. In some areas we can get hard ground conditions, if particularly that area remains exposed for significantly long time, we can expect trypanite ichnofacies over there, and in rare cases we can get a wood ground condition also, where we can get pteridolite ichnofacies. So, any of these ichnofacies associated with this omission surface can point to a transgressive refinement surface. So, colonization of these substrates commonly takes place during a relatively short interval of time, because this is in between transgression. Transgression has already started, and in between the first phase of onlap and the second phase of onlap, we are getting some erosions going on. So, depending on the rate of shoreline transgression, either during or immediately after the refinement surface is cut, we get this kind of substrate controlled colonization. So, depending on what is the nature of the substrate, where this kind of surface are formed, we can get different types of ichnophases associated in different parts. So, following the formation of this kind of substrate controlled ichnophases, the transgressive refinement surfaces are commonly overlapped by the landward shifting marginal marine to shallow marine phases, which actually helps in further preservation of the substrate controlled ichnophases associated with the transgressive refinement surface. The wave refinement surface, which is one of the most prominent surface, this is a scour surface cut by the waves in the upper shore face during shoreline transgression. Now, it can be upper shore face, but it can further extend laterally depending on the wave base of that particular wave. So, this kind of scouring, this kind of erosions by the waves that occurs in an attempt to maintain the shore face profile which is in balance with the wave energy. So, definitely what is the energy of the wave that will control what will be the wave base, and anything between this wave base is prone to erosion by the wave reworking process, by the wave vortex. So, normally it can reach up to 10 to 20 meter of the substrate. So, when this erosion is going on, this wave refinement process can remove substrate as much as 10 to 20 meter height, not more than that, because the wave energy which is dependent on the wave base reaches up to that much. So, it is a function of the related wave energy, which is further is a function of the wind regime which is acting on that particular ocean basin, that particular water body. So, if this is the marginal marine system and if this is the surface, water surface, when this transgression has started, maybe these are the wave vortex. These are the wave vortex. As we know, wave vortex will gradually die out at some depth. So, that particular depth is the wave base. So, any area which is lying below this or beyond this towards the oceanward side, say for example, a wave forming over here will have a wave vortex and that wave vortex will die out within this wave base. So, sediments lying here are not affected by this wave because they are lying below the wave base. Sediments lying somewhere here are not affected by this wave because they are lying below the wave base. But sediments lying somewhere here will get affected because wave base is not dying out and it will try to rework the sediments, it will try to rework the substrate, and that reworking will result in scouring, that reworking will result in erosion. So, as we move from this point onward from the wave base where it is touching the substrate, from that point onward to the shoreline, that entire zone is prone for erosion by these wave activities, wave vortex. So, this wave vortex which is lying somewhere here will have more energy, will have more intensity in terms of scouring, and we can get removal of the materials, removal of the substrate from this area. So, this wave refinement process will be confined within this zone, which is definitely is part of the shallow marine area, and to be more precise, this is more into the shore environment. As we know that the shore face, it is the zone which lies above the wave base, shore face and foreshore. So, dominantly the wave erosions, dominantly this wave refinement process will be affecting the shore environment, particularly the shore face and the foreshore areas. Now, if there is a high energy storm is coming which is having a much larger wave vortex, it will definitely die out at much deeper depth and it will affect the substrate over here, maybe in the shelf area. So, how much scouring will take place will depend on what is the energy of the wave, and the energy of the wave is controlled by the wind, the drag of the wind. So, if the drag is high, if the wind pressure is high, we will get much larger wave vortex, which we call as a storm. So, we can have a storm condition when the wave vortex will be much larger, it will penetrate much deeper within the water column, and it can affect at much deeper part within the substrate. Whereas, on a normal condition, in a fair weather condition, the wave size is much smaller, wave energy is relatively lower, and the wave vortex will die out at some depth, commonly called as the wave base, and the area which is lying above the wave base is prone to erosion. Now, the position of this wave base, it will go on changing as the sea level is changing. Say for example, if this is the same section again, earlier the base level was here, now the base level is rising up and it is reaching up to this. For this particular level, wave vortex was somewhere here, say for example, wave vortex was here. Now, in the same place, since the water level is higher, the wave vortex is now reaching up to this, maybe this is the modified wave base. So, definitely when the sea level is rising, base level is rising and it is encroaching towards the land, shoreline is encroaching towards the land, the position of the wave base will also change. So, earlier the erosional zone under wave condition was this much, and now the erosion is confined over here. So, the position of the wave ravinement surface will also depend, will also vary depending on what is the water depth, what is the energy of the wave. So, the wave ravinement surface is commonly shows an onlapping nature during the retrogressional shift of the facies, and commonly it gets onlapped by the transgressive shore face deposits. So, commonly we get relatively finer sediments coming over the coarser sediments, producing a fining upward succession, and this particular surface may overlie any type of depositional system. This we have discussed in our previous class as well. Say for example, in this section, maybe this part is the fluvial system, maybe this part is the shore environment, maybe foreshore environment, this part is the shore face environment, and this is the self environment. So, now when this onlap is going on, before that some erosion has occurred, erosion has taken place by this wave scouring. So, on this surface now these marine sediments, the self sediments, the shore sediments, they are coming over here. So, what we get in one area, it is the fluvial sediments associated with the scour, followed by the foreshore sediments, overlain by the foreshore sediments. In other part, maybe the foreshore sediments, they are overlain by the shore face sediments. In further deeper part, maybe the shore face sediments, they are overlain by the self sediments. So, we can get different combinations across this particular surface depending on where this erosion is going on. When we are looking at the shore face area, this area is normally above the wave base. So, wave reworking, wave scouring is highly possible over here, and it can lead to formation of a scoured surface, a transgressive ravinement surface, and on that, as the transgression is continuing, self sediments will cover up, will come over here and will get deposited on these shore face deposits. So, across this particular surface, we can get different combinations of depositional systems. In the underlying part, we can get fluvial, we can get coastal, we can get shallow-marine. Whereas, in the overlying part, normally we will get only the shallow-marine, dominantly shore face, in some cases it can be self deposits. So, that is the transgressive package formed above this deposit. So, definitely this surface is highly diachronous, as in the previous example I have shown you that depending on the position of the wave base, we get the surface formed at different parts within the salomarine part. So, this surface is highly diachronous, which will depend on, which is controlled by what is the rate of shoreline transgression in that particular area. In a vertical profile which preserves this entire succession of the facies, the wave refinement surface commonly separates the coastal strata below, which commonly represented by backstepping foreshore and backshore facies in an open shoreline setting, or it can be an estuarine facies in a river mouth setting, and the overlying unit will be normally a shore face and self deposits. So, this already I have shown you in the previous diagram. So, in the fluvial part, in the continental part, the underlying unit, it can be a fluvial deposits, it can be an estuary deposit. So, this fluvial deposit and estuary deposits, they have formed during the early phase of transgression, and then they are associated with the scouring. At the same time, when we are looking into the more oceanward side, more salomarine side, there we can get the coastal area followed by the shore area. So, there we can get a foreshore sediments, which is covered now by the wave erosions, and after that we can get a shore face sediments, followed by that we can get a self sediments. So, definitely this surface, wave refinement surface will form across all these areas, and then after this erosional process is over, the transgression of this entire system starts, and the shore face will try to come over here, will onlap, foreshore will try to come over here on the estuary, estuary will try to come over here on the fluvial, and the self will try to come over here on the shore face. When it continues further, self will further cover up, shore face will come over the estuary, and the foreshore will come over the fluvial system. So, throughout this succession, anywhere we make a succession over here, anywhere, what we get? We get varied facies types, fluvial facies, estuarine facies, foreshore, shore face, self facies below this wave refinement surface over here. Whereas, the overlying facies, it is dominantly salomarine. So, it is either a shore face facies or it is a self facies. In rare cases, it can be a foreshore facies as well. So, in any part of the basin, during the formation of wave refinement surface and after its formation, the transgression process that continues will lead to this kind of contrasting facies architecture. Where the transgressive coastal and fluvial deposits are not preserved, in some cases these coastal and fluvial deposits are not preserved because of this high amount of scouring by the wave refinement process. In such cases, wave reworking of these sediments can reach up to the underlying low stand normal regressive strata, and in very rare cases they can even reach up to the subaerial unconformity. So, in such cases it can be part of the sequence boundary. Say for example, in this case this fluvial system, estuary system that I have shown you, they are forming during the early transgression phase, and we have considered that this erosional surface, it is confined within this transgressive phase only. Say this is the transgressive package that was deposited, that was formed, and above that wave erosion was going on. So, below this what we have? We have the LST package. LST package in the fluvial part, LST package in the estuarine part, in the coastal area. So, if this transgressive package is not thick enough, or if the amount of erosion going on is at very rapid rate, scouring is very high, what may happen? This particular surface can erode this entire material and it can reach somewhere here. So, then it is penetrating into this LST package. If the erosion is even very high, even more than this, it can reach up to the underlying subaerial unconformity and it can merge with that. In that case, the LST deposit is removed. In such cases, the wave ravalement surface will merge with the subaerial unconformity and it can act as the sequence boundary. In stratigraphic sections which are located immediately landward from the shoreline position, particularly at the onset of transgression, many times, looking at this previous example, it becomes very common that the wave ravalement surface has reworked the maximum regressive surface. So, in such cases, the underlying low stand deposits may be a beach deposit, maybe coastal plain deposit, or maybe a delta which are formed during the LST phase, that get highly reworked and it can be found within a fully shallow marine succession. In those kind of conditions, the distinction between wave ravalement surface and the maximum regressive surface, particularly in the marine part of the maximum regressive surface, becomes very difficult, because in both the cases what we are getting, it is an apparently conformable succession, and within this conformable succession we are getting coarsening upward marginal marine succession, marginal marine strata. So, it becomes very difficult. Underlying strata is a coarsening upward, overlying strata is a fining upward. Underlying package formed during LST, which is a coarsening upward, a regressive package, overlying one is an transgressive package, it is a fining upward strata. So, in such cases, it becomes very difficult to distinguish between MRS and WRS, MRS and wave ravalement surface. Rarely, in some cases, occurrence of some lag deposits, commonly we call them as transgressive lag deposits, they can occur along these wave ravalement surfaces and their presence can help us to distinguish wave ravalement surface from other similar surfaces like the maximum regressive surface. If we look into the further inland relative to the shoreline position, when the transgression is starting, the chances of preservation of these non-marine deposits beneath the wave ravalement surface are much higher, because as we are moving into the land towards the landward side, the effect of wave will drastically get reduced. When we look into the landward side, as the underlying packages, they become more commonly the fluvial LST deposits, followed by the fluvial transgressive deposits formed during the early phase of transgression. So, if say for example, in a wave dominated estuary, the wave ravalement is gradually onlapping, gradually encroaching. So, we may get the underlying facies as an entirely fluvial deposits and entirely non-marine deposits. So, both of these options are possible when we look into the further inland in terms of the occurrence of wave ravalement surfaces. So, such transgressive scours, such transgressive ravalement surfaces are commonly associated with rooted non-marine facies. For example, rooted overbank deposits where we can expect formation of firm ground, or in certain cases formation of wood ground, and accordingly we can get glossy fungite ichnofacies or pteridolite ichnofacies. Many times in this kind of scenario, presence of coal beds, they are very characteristic, because within the non-marine succession where very often we get coal beds, particularly in the fluvial overbank areas, these are often gets affected by this transgressive wave scouring, but presence of the coal can stop this down cutting process, because coal is relatively more resilient in nature with respect to wave scouring. So, if wave scouring is going on and it is onlapping, and in the fluvial overbank part it is interacting with a coal layer, a pit forming layer, in such cases the wave ravalement process often stops. So, many a times in many cases wave ravalement surfaces are found directly on top of the xylic substrate or a coal bearing bed. On that straight away we can get the wave refinement surface, as the wave refinement has stopped after reaching this surface. Now, looking into the other side, the other type of refinement surface, which is commonly called as the tidal refinement surface. This is commonly a scour surface which is cut by the tidal currents in the coastal environments during the shoreline transgression. As the tidal currents are commonly more visible, more affected towards the shoreline, so we expect the formation of this scour surface more near to the shoreline with respect to the wave refinement surface. So, depending on the nature of coastal deposits and the magnitude of the tidal erosion, the tidal refinement surfaces may be demarcated by different types of ichnofacies, which may include firm ground ichnofacies, which may include hard ground ichnofacies or wood ground ichnofacies, and accordingly we get the characteristic ichnoforms. In the open shoreline settings, the tidal reworkings in the intertidal to coastal plain areas, it is commonly followed by wave erosion in the upper shore face area as the shoreline shifts in a landward direction during the transgression. As in the previous class also, during our example on estuaries, I have told you that always in a vertical succession, the tidal refinement surface will occur at the bottom part of the succession or in the lower part of the succession, and that will be overlapped by the wave erosional surfaces, the wave refinement surfaces. And if both of them are preserved, we can get them as separate surfaces, vertically separated from each other, where the wave refinement surface overlies the tide refinement surface. This is because the wave process, which are relatively distal with respect to the tidal refinement process, they are gradually encroaching onto the landward direction, and if you make a log, so in the vertical succession, wave refinement surface will come later with respect to the tidal refinement process. So, the tidal refinement surface is generally replaced shortly after its formation by the wave refinement surface. So, this is a very general case, but both of them can get preserved if we have some buffer sediments deposited in between these two surfaces. So, in such cases, what is required? The rate of sedimentation after the tidal refinement process should overpace the wave refinement process. So, you get significantly thicker package of sediment formed, deposited, and as the wave refinement is approaching, encroaching into that area, it is not able to remove the entire package of sediment deposited after the tidal refinement process. Only in those kind of scenario, we can expect that there will be both the surfaces, the tidal refinement surface and wave refinement surface, they are preserved as two separate surfaces. The chances of preservation of the tidal refinement surface are commonly enhanced, as I have told you, in transgressive river mouth settings, where the rates of aggradation of the estuary mouth complex commonly outpace the rates of subsequent wave refinement erosion. When that outpacing of the estuary mouth complex will occur, then only we can get preservation of these two surfaces as two separate surfaces. Otherwise, always the wave refinement surface will superimpose and rework the tidal refinement surface. If most estuarine facies they are preserved, we can get the tidal refinement surface preserved at the contact between the central estuarine mud below and the estuary mouth sand above. Here at this point, I would ask you to refer back to our previous class, where I have shown you this distribution of the different sub environments within the estuary, wave dominated and tide dominated, and there the central estuary, particularly for wave dominated condition, it is a low energy condition where mud will get deposited, and on that gradually the wave reworking process, the estuary mouth sands associated with wave reworking, they will come over. The preservation of the underlying central estuary marge, that will depend on the balance between the rate of aggradation in the central estuary and the rate of subsequent tidal erosion. Because in the central estuary part, we have seen in that example that it is a mix up zone between the fluvial current, river current and the tidal current. And due to this interaction, due to this mixing up, that entire area becomes a low energy zone, relatively low energy zone. So, in that low energy zone, commonly we get deposition of mud, and when it is a mud, definitely the erosion process is restricted. Now, how much mud is deposited? How much is the energy of the tidal current, and how much is the energy of the waves which are gradually encroaching? These factors will control that within a particular estuary, whether that estuary mud is preserved and recording the tidal refinement surface, and on that how much is the estuary mouth sand is coming up, preserving the tidal refinement surface. Based on that, we can get different types of log representation, log manifestations from tide dominated and wave dominated estuary systems. So, identification of tidal refinement surface and wave refinement surface can be best done from estuary systems, because there we can get this distinct zonation in terms of energy condition, distinct zonation in terms of distribution of the depositional systems, which can help us in the identification, which can help in the preservation of these different erosional surfaces at different stratigraphic levels. So, irrespective of the nature of underlying phases, the preservation of a tidal refinement surface requires the presence of estuary mouth complex deposits on top of that. Both the wave refinement surface and the tidal refinement surface are highly diachronous, because as the position of wave base is changing, wave refinement surface, its position will change. At the tidal current is encroaching and it is interacting with the fluvial system, the amount of erosion, the position of the erosion is changing. So, both of these surfaces are highly diachronous in nature, and that changeover with respect to time will be controlled by, or it is commonly matches with, the rate of shoreline transgression. So, with this I will like to conclude. So, transgressive refinement surface, a very prominent surface in sequence stratigraphy, as it is associated with transgression, and during transgression we get a feature of erosion. So, that is why this surface is very special, and depending on the agent, it can be a tidal refinement surface or it can be a wave refinement surface. So, whether a refinement surface will form or not, it will depend on the energy condition of the tide or the wave, how much sediment is supplied into the system, and what is the rate of transgression. And based on that, we can get these two surfaces formed at different zones, different places, different areas at different times during the phase of transgression. So, in certain cases, in very special cases, these surfaces can act as the sequence boundary, as they can separate the regressional package at the bottom and a transgressional finding up package on the top, and in such cases they can merge with a maximum regressive surface in some cases, or they can even merge with the subaerial unconformity in very special cases. So, these are some of the references, some of the books that you can follow for further reading. Thank you everyone.